In activity 3.6, we're going to do some analysis on a type of function called a logistic function, which have this form. A, C, and K are all parameters that are going to be greater than 0. So the first thing we're going to do is calculate the derivative and see if there's any critical points. Well, before we do that, we might want to rewrite L of t as a product. For instance, A times 1 plus CE to the negative KT to the negative 1. It's going to allow us to use a chain rule. So when I do my derivative, I'm going to pull the negative out front. So I'm going to have negative A, which is just a constant, and then 1 plus, I got to leave the inside alone, CE to the negative KT to the negative 2 times the derivative of the inside. Derivative of this part here is just 0. Derivative of this part is plus CE to the negative KT, we leave that alone, and then times the derivative of the exponent, which is negative K. So, let's see what this is going to simplify down to. Now this is going to go, I'm going to go ahead and write that in the denominator. 1 plus CE to the negative KT to a positive 2. And in the numerator, I have a negative A, but also times a negative K. So I'm not going to worry about that. The negatives will cancel each other out. And I'm going to multiply by that C as well. So I have an A times this C times this K. It's going to be positive again because the negatives were canceling each other out. E to the negative KT. Now, remember, we set the derivative equal to 0 and solve. Well, there's only two possibilities for getting a 0. First off is e to the negative kt. Well, that's an exponential function with a horizontal asymptote at 0. It is never equal to 0. Now, remember, for critical points, it could also be a point of discontinuity, so we got to check the denominator, 1 plus CE to the negative kt. Well, this part's never going to be 0, and we're adding 1 to it. So, this is going to have a horizontal asymptote at 1. This is also never going to be 0. So we actually have no critical values for this particular function. For part B, they actually give us the second derivative, and then find all the values of t for which the second derivative is 0. So we're going to set this thing equal to 0. Now similarly, this part here will never equal 0, and this part here will never equal 0. The only thing that could possibly be 0 is this numerator here. So we're going to set that to the arguments on these two are the same as they were for the first derivative. CE to the negative KT minus 1 equal to 0, and we're going to solve. So we got CE to the negative KT equals 1. Divide both sides by C. We have e to the negative KT equals 1 over C. Now this can be rewritten using a natural log, right? A log base e. So negative KT equals the natural log of 1 over C. Last, to divide both sides by negative K. And we've got our t. We've got our critical value, because those will cancel. T equals ln of 1 over c over negative k. So we can do a number line analysis and figure out where our function is concave up and concave down. So this is the point ln of 1 over c negative k. Now if you remember how natural logs work, or logs in general, log of anything smaller than 1 but greater than 0 is negative, and natural log of anything greater than 1 is going to be positive. So in trying to determine what our concavity is going to look like, to the left of this point, if we're going to be inputting values into our second derivative, and we're only concerned with this part here, this will always be positive, this will always be positive. So this is the only thing that's really going to make a difference. Well, if we use t values that are smaller than this, then what's going to happen is we're going to have a number here that's going to be less than 1. Excuse me, that's going to be greater than 1, because we're going to be using the small t values. It's going to keep this number large. The larger the t values get, the smaller this gets. So t values smaller than our critical value are going to force our second derivative to be positive, because this is going to be really small and c is going to be really large comparably, and so c minus 1 is going to be greater than 0. Similarly, if we're over here, if we use values larger than this, we're going to find that t values larger than that is going to make this piece really small, so small that this whole thing is going to be less than 1. So this is going to end up being negative. So L is concave up from negative infinity to ln of 1 over c over negative k, and it's concave down from ln of 1 over c over negative k to infinity. So here's our interval for up, and here's our interval for down. So we can actually figure out the concavity from our number line analysis. Now, part C is asking about the limit of this function as t goes to infinity and negative infinity. So the limit as t goes to infinity of a over 1 plus c e to the negative kt. Well, let's see what's going to happen. As t goes to positive infinity, this piece here is going to go to 0. So we're going to have a over 1 plus 0. So this thing is going to go to a. Now, we go to negative infinity. This is one of the very interesting pieces about the logistic function of a over 1 plus c e to the negative kt. As t goes to negative infinity, this is going to negative infinity, but a negative times a negative is a positive infinity. E to the positive infinity goes to infinity. So we've got something in the denominator that's going to infinity, where a is just a constant. So as the denominator goes to infinity, that's going to pull the whole thing to 0. So we get a function with two horizontal asymptotes, and we'll be able to see that from the graph. For part D, we're actually going to go back to the sheet we were just on, as it asks us to find the critical point. Well, we know, the inflection point. We know the inflection point occurs at this value. So let's see what happens when we stick that into the original function. So we're going to calculate L of the natural log of 1 over c to the negative k. Now that's going into the original function. So back to our original function, we have a over 1 plus c e to the negative k, and in that input is going natural log of 1 over c over negative k. First thing you might notice, these can't cancel out right away. So we have a over 1 plus c e to the ln of 1 over c. And if you remember your properties logs, e to the natural log of 1 over c is just 1 over c. So a over 1 plus c times 1 over c. Those cancel, and it's just 1 plus 1, or a over 2. So we have an inflection point for our logistic function at the point ln of 1 over c over negative k, comma a over 2. Notice there's no x in here, so this inflection point is based on those coefficients a, c, and k. So based on those coefficients, we can always figure out what our inflection point will be for this family of functions.